presentation. I'm going to present the company, Vibrance Technologies. It's a company that was formed only 4 months ago with a merging of 3 different companies that are Prince International. It was a company focused in the additives and mineral additives and the brick industry, main. Then Ferro, that was our former company, that it was focused in the porcelain enamels, fruits, and also in pigments, in organic and organic pigments. And ChromaFlow Technologies, that it was a company focused in the coatings sector. So these 3 companies merged 4 months ago and formed Vibrance Technologies. Some numbers about our company. Well, the headquarters are in Houston, Texas, and we are mainly focused in the American market with more than close to 50% of the business in the Americas, but and also important here in EMEA, around 30%. Our end market, our focus our targets in the end market are mainly the building and construction and industrial applications. So we have, what we do is try to give solutions to these different sectors we are intermediates in the industry, so we are giving solutions mainly to this sector. So we prepare minerals and materials like biocides, dispersing agents, fillers for the coatings, mainly for the coatings applications. We also transform minerals. We do have different technologies to transform minerals, furnaces, high temperature reactions, precipitations, milling, sieving, and so on. Then we deliver color solutions. That it's we provide inorganic and organic pigments, but also additives for the coatings or the buildings and plastic industries. And also we provide support and innovation to our customers. So we have application laboratories to try to develop solutions for our customers, tailor-made solutions in most of the cases. Our company is divided in 3 branches. Is advanced materials, that it's focused in the additives, the mineral additives, and also an important presence in the batteries and electronic materials sector. Color solutions, that is focused in the color, I mean, in dry pigments, but also in liquid dispersions. And finally, performance coatings, that it's mainly the porcelain enamel and glass coating solutions. I'm forming part of the color solutions because we are doing inorganic pigments here in Barcelona. In Barcelona, we have a laboratory, an R&D laboratory, with close to 20 people working on the color solutions, especially in the inorganic pigments sector. Again, we are all over the world. Important presence in the Americas with 28 sites of the total 64 sites in the whole world, but also in Europe and EMEA with 25 sites. And color solutions, what do we do? We prepare liquid colorants, organic and inorganic pigments, pigment dispersions and performance additives, and chemical dispersions for all these different sectors: architectural, construction, industrial, inks, and so on. In this case, we come from Ferro, and this is the most important pigments we were preparing at Ferro in Barcelona, but also in the factors related to us. First, the ultramarine blues, violets, and pinks, iron oxides and ferrites, mixed metal oxides, or also called as complex inorganic color pigments, corrosion inhibitors, chrome yellows and molybdenite oranges, and basic gram sulfate. Highlighted in yellow, I put the ultramarines and the corrosion inhibitors because these are the 2 pigments that we studied in Alba some years ago. So let's start with ultramarine pigments. The ultramarine blue pigment is this nice color. I like it very much because I work directly with this color. And it is a complex structure. It's an aluminosilicate with sodium and sulfur in the structure. So the skeleton is silicon oxygen and aluminum oxygen bonds that are forming what is a sodalite structure type. And this sodalite has a vacancy that it's called a beta cage, where sulfur is embedded into these cages to form the color. So the color is produced by sulfur species into this chemical structure. Several sulfur species are embedded into these beta cages. Some of them give color and some of them not. And this is very important to know the presence, the qualitative and quantitatively, the presence of these different sulfur species into the cages to correlate this with the final quality of the product. Ultramarine blue is spread in different sectors. Here you can see, for example, it is mainly used in plastic sector to color plastics, but also as an optical brightener, to transform white, to make whites whiter and to make blacks blacker, to increase the whiteness and the jetness of the applications. But also it has some presence in the coating sector, in the buildings, so we have, for example, products especially developed for the building sector, and also in the cosmetics. Ultramarine blue has, as I told you before, the sulfur species into the ultramarine blue is the most important part to control or to tune the color of the pigment. So ultramarine blue has a species that is 3-, that this is an anion radical species that gives this intense or this deep blue coloration. On the other hand, the ultramarine violet and pink, it is made through a combination of several different chromophores. S3, the blue one. S2 is also another anion radical species that gives some yellow color, and the S4 that gives some red color. So the combination of red and blue gives the violet, and reducing the blue, increasing the red. At the end, you obtain the ultramarine pink. So the color strength of this pigment is a function of the presence of the different sulfur species, the amount of this species, the crystallinity of the sodalite structure type, and then the presence or not of secondary phases. In this case, with conventional X-ray tools, the characterization, especially the characterization of the sulfur species, is not enough, the conventional X-ray. And this is why we contacted in 2015 with ALBA to start to deepen the knowledge on the ultramarines, trying to correlate the chemistry and the structural details with the quality of the final pigment that we are producing and selling. So, as I told you, in 2015 we contacted with ALBA, and we have we did some technical meetings to define the problem with the experts in ALBA, and then from 2015 to 2017 we sent several samples to be analyzed in these 2 lines. First in the MSPD to run synchrotron X-ray powder diffraction studies, and trying to have a good adjustment of the structure and microstructure of our pigments, and also the presence of secondary phases, because many times the secondary phases are less than 2% in composition. So we need with conventional techniques, sometimes we are not having this information. And then the second part is to study the sulfur species. For this, we go to class to run some sulfur KH X-ray absorption to do a speciation of the sulfur species in the ultramarine pigments. The idea was have more detailed structural characterization of our pigments to define first the best fabrication procedure to enhance the properties of our pigments and to increase our margins and so on. and then how to obtain the desired colorimetry by a combination of these different chromophores. So this was most focused in the violets case, but look for the best combination of the three different chromophores to improve or to enhance our pigments, to the interest in the market, and even to develop new pigments. In the MSPD beamline, we do refinement of all the samples that we send to ALBA. All of them show the distorted cubic laserite unit cell, distorted to monoclinic. We have the different cell parameters, and also we did the quantification of the secondary phases. The pigments we produce are all around 97 to 98% of ultramarine. And then the secondary phases are pyrite and sulfur, around 1%. So we could have a different compositional structures, and we compare the quality of the pigments with the presence or the absence of the secondary phases and the cell parameters of the ultramarines. Then in the class, what we do is the X-ray absorption of spectroscopy to do the speciation of the sulfur species in the drug gauges. For this, when we contacted ALBA, they recommend us to run these experiments because it was the only way to try to determine or to run this speciation of the sulfur. It was, I think, the first time that they were doing this kind of experiment, so we were like the first test. And the first thing we did is study how our samples behave in this technique. So we ran several experiments, tried to see if the samples are stable enough to do this speciation, and the answer finally was yes. The ultramarines were stable under this kind of radiation experiment, so we could continue to the next step. For this, we recorded several spectra with this technique, and we were able to determine what was the part that was related to the blue chromophore, to the red chromophore, and to the colorless chromophores. So we have a comparison amongst several different samples, and we could correlate the presence or the relative presence of these chromophores with the quality of the final pigment. So it was really interesting for us because it was the only or the first time we were able to have a speciation of the sulfur species, because you have to bear in mind that the ultramarines, the molecular weight of the ultramarines are around 1,000. Around 1,000, and the sulfur species it's 32 plus 3, so it's 96. So it was less than 10% the weight of the sulfur into the structure. So in this case, these studies allowed us to do some fine tuning in some of our synthesis procedures in the lab and also in the factories, to produce pigments with higher tinting strength than the ones that we were producing in the past. We finished this study in 2017, and also as we had a very good collaboration with ALBA staff, we continued with studying another kind of pigments, the anticorrosive pigments, in this case, the zinc molybdate corrosion inhibitor. In this case, the study was shorter, but it was focused in the REACH registration of this pigment. The zinc molybdate, to be registered in the ECA for its distribution in Europe, needs to be a pigment with less than 1% of molybdenum trioxide, which is a CMR, carcinogenic, mutagenic, and reproducibility, and that affects the reproduction product. So we had to as we wanted to sell this product in the European market, we had to demonstrate that this pigment has less than 1% of the molybdenum trioxide. For this, we came again to MSPD measurements, and we tested several samples with different synthetic ways. So we produced the zinc molybdate through different with precipitation or calcination reactions, and then we were able to select which was the most proper way to produce the zinc molybdate with less than 1% of molybdenum trioxide. Again, the results allow us to develop also a combined method, because it is quite difficult for the industry to use the synchrotron techniques as a daily test, and many times you have to certify a lot of lots, industrial lots, to be sold in Europe. But we were able at this moment to run a conventional X-ray diffraction test and to do some calibration of this conventional X-ray diffraction test, thanks to the results obtained with MSPD measurements done. And to end our experience in ALBA, was, as I told you, it was very, very nice, very good collaboration. It opens to us the possibility to solve industrial issues with technological techniques that are not in the industry. So for us, all the knowledge that we got from these experiments, it was very useful for us to develop our pigments and to improve and to have a competitive advantage in the market. How we do it? How we did it? We organized regular meetings, and also the ALBA staff were also giving or sharing their experience in the characterization techniques, and we had nice discussions and follow-ups of the project. And also, we are always assisted with people that knows a lot about all this kind of experiments and all these techniques. In fact, we sent the samples, and we also were requested if you want to come to here on ALBA to see the experiment, how it works and how it goes. So the collaboration was really nice. And at the end, we did a final roundtable. We shared the experience, all the results. We discussed, and also we correlate or we get the information to do the correlations in our labs. So at the end, the result was very, very good for us, and I think I am here because we are very proud of this collaboration, and if in the future there is another possibility to collaborate in another project, for sure we come back again. And that's all. Here you have our web page and my contact and another guy in the R&D laboratory. So again, if you want to contact to ask for more details, something that it can be explained, I don't have any problem to answer to you. Thank you very much.
Thank you very much, Jordi, for the presentation. If there is any question?
Not a question, I have a second talk. Ultramarine blue is not a very stable pigment. And we investigated that in very detail, and the interaction with different supporting materials, clay, for example, and things like this. And I hope that you analyzed, you are not interested in what are the correct locations of the sulfur. We went one step further in our analysis, because if you differentiate the spectra, you can see how many different species you have. There are more than 3. Apparently, not just, as we both know. And we looked also in the aging process, which ones are disappearing first. We did that not for industry, but for archaeology, because ultramarine blue is in archaeology a very important pigment. And we never published it, but we have dozens of spectra going a little bit beyond what you showed, but I suppose you have also more than you showed us.
Okay, thank you. Well, I want to say ultramarine is a stable pigment. It depends on the environment, of course. For example, it's not acid resistant, but we developed an acid resistant grade to cover the ultramarine blue with something that makes some resistance against the acid. And with clays, more or less the same. We have an especially developed solution for clays and cements sector.
We didn't do in situ. You can, of course, look for the edging in situ. We haven't done that, but we looked for the various support structures, and the people were interested in the aging process because we're not protected. And is there any chance for restoration? Because it was archaeology and things like this. And we did that also for quite a long time.
Thank you.
Challenging.
Okay, thank you for sharing experience.